Hello, this is Group 4.1, and this is our Embodiment Design phase video. To start with a quick introduction, my name is Dallas Hamilton.
I'm Dia Mahmood.
I'm Bilal Yassini.
I'm Ahmed Ali.
I'm David Ahmad.
I'm Matthew Tomlinson.
Now, to just give a quick recap of our background, we are presenting ourselves as a young up-and-coming team that's brought in by Andretti Global to work on this new, fresh design for a Formula E car that they'll be running. We want to make a prototype model scaled down that we can present to the team heads here. Now, when we looked at market examples, we took a look at other models of Formula E cars, and we again noted that the major needs are a high speed and a sleek body that matches the rest of the competition. Now, what we didn't see was a multi-speed transmission, which we will be implementing in our design. And here is a quick list of our stakeholders and how we rank them.
Next is objectives. So for objectives, we have our requirements here. So these are things like safety and compliance, which is restrictions of our size and the safety aspect of it. Reliability, so it should operate for a certain amount of time without resetting. Controllability, so this is it being able to drive for 5 minutes without any interruptions and no sliding on corners when turning. Collision avoidance, which uses the ultrasonic sensor to stop before 50 centimeters of a wall, and the cutoff will be half a second before that. Uh, for performance, it should have a minimum speed of 3 meters per second, and for aesthetic quality, it should have an enclosed wheel profile, aerodynamic body, and enough space for sponsor space. Next is the constraints. So things like it should include all of the subsystems such as steering, transmission. It should use the parts given. And for performance, it should be able to ride up a 15-degree ramp, uh, have a 5-minute run for 2 seconds. It should have stability. Uh, it should be reliable, so it continues for 5 minutes and withstand a 2 kilogram load. And it should be modular, so things can be disassembled and be taken out. So for the chassis, it's the functions that are in it are that includes covering for the electrical components in the rear. It covers the top of the steering and suspension systems in the front and has space to allow for removal and replacement of parts, giving it modularity.
When it comes to transmission, we're moving forward with a 3-speed sliding mesh gearbox that takes power from the motor to an input shaft that has 3 static gears here that will interface with a corresponding gear along the output shaft, which will be able to be moved while the car is stationary. And these 3 speeds will become coming from this 3 sets of gears here, and they will be translating to the rear axle. Couple example gears that we've worked up in SolidWorks.
So for the steering, we're going to use a servo motor and the attachment arm included, and that will be connected to a push rod, uh, connecting to 2 tie rods that are attached to the wheels. The rotation of the servo motor is going to turn the wheels to the right or to the left. It has a total of 5 points of rotation.
So this is a front geometry of a suspension, and here you can see the shocks are uh, packaged inside the chassis, so it doesn't mess with the aerodynamics outside of the car, and that will work on a push and pull rod type suspension. I've also listed out some of the measurements for the suspension, like the wheelbase, which is the distance between the front and the rear tires. And based off that, we can get our front track and our rear track. The KPI and caster angles is just for the feel when you steer the car, and the cambers are there to help performance when cornering the car. And here are some CAD models that we have for the suspension, the control arms that attach the wheels to the chassis and the steering knuckle that joins all the suspension components and steering components together onto the wheel hub.
All right, so move on to electrical and control systems. Most of it will be the onboard system, using most of the materials provided, such as the Arduino, which will be kind of the brain of the car, power, mechanically the breadboard. We also have of course, the motor driver, and the motor servo to help control like kind of finer steering. Um, and then we also have for our safety subsystem, the ultrasonic sensor to detect obstacles, LEDs and buzzers to give heads up at certain predetermined points, as well as resistors to ensure no parts are blowing out. And then for our user interface, we'll be using the IR transmitter for remote control for steering of the vehicle. Next, we have our design calculations.
So for the calculations of the chassis slash body, we see here that we have a free body diagram, which shows all of the forces acting on the chassis and the body. So here, the chassis will have weight, which will be acting onto the wheels, which will then cause the wheels to have a counter force. And also the payload and the electrical and motor components will also be acting down on the chassis, creating shear stress on the top. On the axle and the wheels, when the wheels are rotating, it'll be creating a moment, a resisting moment for the axles, so that will cause some stress on it.
For the transmission, we've looked at relating the gear ratios to each other with the specific interactions relative to the 3,500 RPM of the motor. We have, for the motor to the input shaft, and then the three gear states that we'll have, and then from the output to the axle. And relating those down, we get 30 to 1 for first gear, 18 to 1 for second, 12 to 1 for third. And with these final RPM values, we believe that we'll be able to get a substantial torque difference between first, second, and third gear, and a difference in speed as well.
So for the steering, we're using zero Ackerman steering. In essence, both tires are going to turn at the same angle. It's going to be less ideal for turning radius, but it's excellent for prototyping due to its simplicity. For the steering angle, it's just going to be the wheelbase over the turning radius multiplied by arc10.
So we have our suspension calculations. As I said, we took the wheelbase and we'll multiply it by a uh ratio to get our front track and our rear track ranges. And well, what these front track and rear track um measurements do compared to the wheelbase is make it handle better in a straight line and in steering around corners.
And last but not least, we have our electrical calculations, mainly focusing on energy, power, and resistance. So the first one, just seeing how much like energy and watt hours we have based on specifications of the 12-volt battery, and then using that as well as our expected current, if it's the maximum current, to get a total of 3 hours, which make sure that we can operate for at least 3 to 5 minutes as required. For power, using the mass of 2 kilograms that is required, as well as the 15-degree angle, we calculate the force, and then use that multiplied by the velocity, minimum velocity of 1 meter per second to get the necessary power for that. Of course, this is just like the minimum values. And then also using resistance, knowing that different color LEDs have different necessary voltage, and then using that to find the resistors necessary for each of the LEDs when used. Next, we have prototyping.
So for our prototyping and fabrication approach, we'll be printing from PETG and PLA and incorporating TPU for things that need to be more flexible, like tires. Uh, and for testing, we have to focus on live assembly and looking at how the car moves in real life with all the physical components, how they work together. And for our physical performance, based off our wheels and our gear ratios and the RPM of the motor, we feel like we can get to around 18 to 22 kilometers per hour, and it should be able to climb a 15-degree incline with our gear ratios as well. And in conclusion, the impact of our embodiment design is that we've quantified how we're gonna make our wheels and how we're gonna improve handling and the materials um and chosen how which parts will be printed with which materials. Some remaining risks and improvements is gear wear when we're running at high speeds for a long time. We need to fine tune the steering as well. We're starting right now with a zero Ackerman, as we mentioned, and our next steps is CADing all of our parts and finalizing tolerances and printing and iterating. So